So in this video, we're going to look at 2019, number 6, BC question, the Taylor-Maclaurin question for this year. They give us a function f has the derivatives of all orders for all real numbers of x. They give us a part of the graph of f to the right, and they tell us that there's the tangent line is also given. So other selected derivatives are in that table, so the second derivative, the third derivative, the fourth derivative are all of those values right there. So this n is replacing that n right there. So for part A, they want us to write the third degree Taylor polynomial for f about x equals 0. So secretly, this is Maclaurin, but Taylor covers all of it, so that will be fine. So we're going to write our general Taylor for a third degree polynomial first. So p of 3 of x equals f of 0 plus f prime of 0 at x. Second derivative goes with the x squared term. Third derivative goes with x to the third term. And of course, we have those factorial adjusters on there as well. So really, this question, you need to find those derivative values, if you will. So the first two, we're going to use the graph. And then the last two, we're going to use that table. So the first two, f of 0 would equal 3. That's just the ordered pair on this graph. So that's just that ordered pair right here. And then to find f prime of 0, that's the slope at -2, we'll use the slope of the tangent line at that point. So it looks like it goes down 2 and over 1. So down 2 over 1 would be the slope, so -2 is the f prime on this one. Second derivative, they give me in the table, so we're going to use the table to see that. At the second value for n, or the second derivative, the value is 3. And then at the third value of n, plug in a 3 there, it would be this weird -23 over 2. So those are your derivative values, and we're going to plug those in to their representative spots. So let's see what that would look like. And you can actually leave your answer like this. You don't have to simplify it, but it doesn't hurt. So we have a complex fraction on the last term, so we can clean that up just a little bit. So my answer would be something like that. For part B, they want us to write the first three non-zero terms of the Maclaurin series for e to the x. That would just be from memory. And then the second part, write the second degree Taylor polynomial for e to the x f of x about x equals 0. So that's where this will be a little bit tricky. So the first part, we're just going to write the e to the x function. And it is 1 plus x squared over 2. We could keep going following that pattern all the way down for e to the x. That is one that they would like you to know. The second one is they want us to write a second degree polynomial for e to the x multiplied by f of x. So let's pull in that f of x function that we did from part A. So that looks something like that. Now, I put too many terms there. I really only needed to go to the second power because I only want a second degree, so I won't need to use that x to the third, but I snuck it in there anyways. So really what they want us to do is multiply e to the x and f of x together. So we're just going to distribute. We're just going to do old school distribution. We're going to take this 1 right here, and we're going to multiply it by all of the terms on the inside here. So we're going to go ahead and do that. And then we'll distribute the x into all three of those. Although we won't need the last one right there because it'll be a third power. So we're only going to stop, or we're going to stop at that second power for this one. And then I'll need to distribute the last term in here. I'll only have to do it to the front. I won't have to do this one because that will give me x to the third power. So we don't need to go quite that far. We could, but they only want a second degree polynomial for this. So if I distribute the 1, basically I'm copying the first 3, that 1 distributed. So this chunk right here is from the 1 distributed. And then the x distributed gave me these two terms. And then the last x squared over 2, that distributed in there gave me this term. Now, I didn't do a full distribution. Once again, I only needed it to the second power. So just added my like terms here together. So I have a 3. I have a couple x terms together, and then I'll add all the x squared terms together. So it should simplify to 3 plus x squared. In part C, they say let h be the function defined by h of x equals the integral from 0 to x f of t dt use the Taylor polynomial found in part A to find an approximation for h of 1. So they want us to plug in a 1 for the x's here. And we're going to use f of t. Really, that's just our f of x or p of x function from part A. So I'll go ahead and bring both of those in here. But h of 1 equals the integral from 0 to 1. The x gets replaced by a 1. And then that really is the polynomial function I used. I did do it in terms of t because they did say f of t dt. So if I want to approximate h of 1, I just need to evaluate this antiderivative. So I'll just power rule the inside of that. Nice part about polynomials. So 3 goes to 3t. Minus 2t, power rule that all the way down the line. And then I'll just plug in my upper bound minus my lower bound. So a 1 plugged in to all of those basically just makes the t's go away. So h of 1 would equal 3 minus 1 plus a half minus 23 over 48. And then I did sneak in a minus 0 there because that's the lower bound plugged in. If I plug in a 0 for all the t's, it would just go away. So just add those like terms together, simplify, common denominator is 97 over 48. They're okay if you leave the answer as all of this part right here on the non-calculator, but it wouldn't hurt to simplify. And part D is kind of a mouthful. It says it's known that the Maclaurin series for h converges to h of x for all real numbers x. It's also known that the individual terms for the series for h of 1 alternate in sign and decrease in absolute value. That tells you it's an alternating series and that it converges essentially. Use the alternating series error bound to show the approximation found in part C differs from h of 1 by at most 0.45. So this is that alternating series error bound, and that is using the first term that you did not use. So I have to first think about which terms did I use. So for my polynomial function x, I went to the third power because that's what they wanted us to use for that first part. That means that the first unused term, which I don't have yet, it would be the next term in that polynomial. And so I need that x to the fourth term is really what I need. And I'm going to use that to try to figure out what the error would be in this. So the fourth derivative is 54 from the table. And so that means that the fourth power term would be the fourth derivative, x to the fourth over 4 factorial. So really that 54x to the fourth over 4 factorial, that is the first unused term in that polynomial. I used the first up to the third power, so I'm going to use that fourth power in the next term to find out what my error is going to be. So I'm going to go ahead and use that for my h of 1. So essentially I'm just building another approximation for this, but this approximate error bound, it's always the absolute value of the first term that's not used. So I'm going to go from 0 to 1 on that first unused term to find out what my error would be. So I'm just going to power rule that, just raise that by a power and divide by the new power. And upper minus lower, and we're good to go. So 54 over 5 factorial. And you can reduce that, simplify that. I think you can take a 6 out of both of those. I believe you get 9 over 20, which is 0.45. So you've shown that is the error, the max error that it is going to be.